So in this first video on AS statistics, we'll be going through how to use statistics to problem solve. So we're going through the types of data you can encounter and also working through the problem solving cycle. So the types of data we can have now, before we go through these particular examples of types of data we can have, what I'd always recommend is that you always have some examples in your head, just try and make it easier for you to explain, because obviously when you're remembering things and definitions, sometimes it's quite difficult to get the wording right or remember it word for word. But however, if you relate it to an example, it makes it easier for you to understand, also to differentiate between the different types. So one of the types of data we can have is what we call qualitative data. Now qualitative data sounds like quality, and so if you're describing the quality of something, you're usually going to represent that with a word. So things like amazing, awesome, rubbish, maybe not rubbish because it's not really the best word to use, not very good or poor quality, etc. Now quantitative data sounds like quantity, so you're thinking about how much something is. So that's data that's represented numerically. So an example of qualitative data would be the colours of cars, the favourite choice of subject, and quantitative data would be an example of would be age. Let's go for average grade levels, test scores, etc. Now another type of data we can have when we know that data is quantitative is discrete data. Now discrete data is data where numbers can be only certain numbers within a given range. So things like numbers on a die can only be certain numbers, age can only be certain numbers to a particular point if you think about whole numbers. Now the key thing that people tend to forget is discrete data, they think whole numbers. Now it's not necessarily whole numbers, so I could have shoe sizes in the UK where we could have half sizes, dress sizes, anything within a given range. So if I was going to look at shoe sizes here in the UK, I would have for a male, I would say any ranges from, let's say, size 4 to size 18, maybe if they play basketball, without sounding too stereotypical there. But I wouldn't expect, and I could have half sizes within that range, I wouldn't expect anyone to have a shoe size of, let's say, 56 or 22.37. So it's only numbers within a given range. Now continuous data, however, that's data where numbers can be any number within a given range. So things like height, and now depending on the instruments you're using to measure the height, that could be any number, and also depending on the units you're using, could be any number within a given range. So things like weight, height, etc. can give you an example of this continuous data. Now in terms of discrete and continuous data, those will probably come up more when we look at probability distributions, and also looking at graphs and the types of data you can use with particular sort of calculations and diagrams. So it's important that in maths that there are several types of diagrams you can use. I'm sure you can think of many that you've done in your sort of mathematical learning beforehand, of like pie charts, bar charts, line graphs, cumulative frequency diagrams, etc. And you've always probably wondered, why can't there just be one? Well, there is one, because one will always be better than other graphs depending on the data you are working with and what you're wanting to draw conclusions from. So anyway, going back to the process, let's have a look at using statistics to problem solve. Now when we are problem solving, there is a problem solving cycle that we need to work with. So the first one is problem specification and analysis. Stage 2 is information collection. Stage 3 is processing and representation. Stage 4 is interpretation. And what I'm going to do now is I'm going to go through those 4 stages and explain to you what it is and what they both entail. So with regards to problem specification and analysis, so this covers the preliminary work at the start, beginning with analysis of the problems to be solved or the question to be investigated. So also, if we were dealing with a hypothesis, so if you're not too familiar with the word hypothesis, an hypothesis is an opinionated statement that you are looking then to prove. So the first step is to be clearly exactly what you want to achieve. Then you have to plan how you're going to go about this, and a critical question is what data you need, but also you need to be clear on how you're going to collect them and what you expect to do with that data once you've collected it. And the ideas involved are going to be worked through in this particular presentation. So the second stage is information collection. So this often involves taking a sample from all of the possible data or the parent population. However, sometimes you are able to collect the whole population, such as 100% sample is called what we call a census. So if you've asked the whole entire population, then we can say that this is a census. And like I said, there are many different ways in terms of collecting that sample, and there's a video that I've done on Statistics 1 on sampling methods. Now the next stage we look at is processing and representation. So there are several tasks under heading of processing and representation. The first of these is cleaning the data. So what we need to do is work with by cleaning the data, look at particularly outliers, missing data, anomalies. So outliers are results that are going to skew our results. So numbers that are ridiculously big or ridiculously small. Factual results. So for example, if I'm looking at the average age of a party, I might want to include sort of not include any newborns, or without sounding too bad, ridiculously old people. So people in the 90s, maybe in the hundreds, unless it's their party, obviously. Long may they live. So missing data are data where you've collected the data but answers have been left unanswered. So for example, if you've done a survey and someone has decided not to answer that question, it might be missing. The person collecting it may have missed that question out, etc. And anomalies are basically the difference between anomalies and outliers. Anomalies is where data has been entered incorrectly. So for example, if I'm supposed to write 17 but instead it looks like 77 because the ones look like 7s, then that'll be classed as anomaly. So it's important that we look through our data to look out for these three things, because obviously they could then skew our results in terms of calculations, and obviously going on from diagrams that we could potentially use. It's also important looking at what diagrams we're going to use. As I mentioned earlier, there are certain diagrams that we're best suited for the data that you're working with, or to prove or disprove your hypothesis that you're working with, which again, there'll be another video on the types of diagrams and their pros and cons for doing just that. Now in terms of representing the raw data, I kind of know that I'm going in reverse order. So it's a case of, are you going to use like a tally table, are you going to record it on paper, or are you going to record it on a spreadsheet to make it easier for you to calculate? Now the last and final stage is interpretation. So with regards to interpretation, this is where you draw your conclusions about the situation you are investigating. You would typically have carried out some calculations already, and this is where you explain what they tell you, and the investigation will not, however, be complete until you've reported what you found in words. So finally, you ask yourself if your findings are realistic and if they answer the question you were addressing. If not, you'll have to do some further work, and this may involve collecting more data and repeating stage 2, 3 and 4, or collecting a different set of data, and so repeating the whole cycle again. So it's just a case of looking at improvements, and as you can see on there. Now one thing I would probably stress to you is that whenever you are drawing a conclusion from a statistical sort of investigation, it's important that in your sort of conclusions you include these three things. So one is a mathematical statement, so things like on average this is true, or my calculation showed this. Then you want to then show your mathematical evidence. So in the first stage of mathematical statements, you can use as much mathematical terminology as you like. The mathematical evidence is the calculations and the graphs that you've shown that support this claim. And then the real life meaning is, well, this is where I usually tell my students to, well, what does this mean? Now, sometimes you might be reiterating the mathematical statement if it's not using that many mathematical words. But if it does, you kind of just translate it to, let's say, explaining it to someone of a non-mathematical background. So how I always say, it's like, how do you explain it to a younger sibling? So, and again, you also want to be talking about biasness as well. So in stage sort of 2, you want to be looking at reducing the amount of biasness, but also in the final stage you also want to be talking about biasness. So did your data, was it acceptable for including any bias in your data? Could that have affected your final conclusions? So it's worth discussing this, and there is nothing wrong with having a fault in your investigation. Sometimes it's kind of encouraged because you always want to find improvements, and every sort of investigation could always be improved, whether it's increasing the sample size, or maybe doing a different diagram, collecting the data slightly differently, doing a different sampling model. So it's important that you leave a bit of room in terms of how to improve it, because obviously That's what makes the world turn round and improve things. So just to summarize, this is the general problem solving cycle. So if you can remember this cycle, you can kind of relate it to what it actually means. And the titles for this is quite self-explanatory. So problem spec and analysis is identifying the problem, what your initial plans are going to be, and talking about what potential issues you're going to have, what biasness you're going to encounter. Information collection is all about the sampling methods, how you're going to collect the data, what you're going to do with the data, how is it going to be used. Processing and representation, again, is physically collecting that data, representing, doing your calculations, drawing your diagrams, and interpretations is all about drawing your conclusions. So hopefully this makes a little bit of sense, and if you have any issues, feel free to drop me any questions at 162maths@gmail.com.